Hello, this is Dr. Muhammad, and this is Engineering Mathematics class, and I'm going to talk today about the non-homogeneous equation, undeterminate coefficients. I'm going to talk about the undeterminate coefficient method for the solution of the differential equations. So I'm going to start today. Let's go. This is, as we said many times, that the non-homogeneous equation, it has different ways for the solution. So whenever that we are going to solve, I think that we need to look to the form of the homogeneous equation itself, and we try to find a proper way for the solution. One of these proper ways is the undeterminate coefficient. And this undetermined coefficient, we are going to talk about it in detail, but remember well that the way that we are looking to the non-homogeneous equation is very important in order to determine the way of the solution. Okay, so now let's go and dig deeper into the method of undeterminate coefficients. We will discuss a second method for finding a particular solution of the non-homogeneous equation. So now today our main target is going to find the particular solution. If you remember, last time we said that we need to find two linearly independent solutions of the associated homogeneous equation and one particular solution of the non-homogeneous equation. So now this is a second method for finding the particular solution of the non-homogeneous equation, which however applies only to the constant coefficient case. This means that we are going to deal with this shape, and this is what I confirmed in the beginning, that the shape itself of the non-homogeneous equation is going to tell us which way that we are going to follow for the solution. So here, as you can see, we have constant coefficients for the left-hand side, which is, if we can call it, the homogeneous differential equation or the homogeneous equation. So this is constant coefficients. We have a, b, and we have here 1. So this means that this side is having constant coefficient. And on the right hand side, it is f of x here. Okay, so the point is this f of x is very important for us, because the main idea here that sometimes we can guess a general form for yp, the particular solution, from the appearance of f of x. Now this is the point here, that f of x is going to play a central role and the solution of the undetermined coefficients. Okay, so these are the two conditions. Here it is constant coefficient, and for the f of x we are going to tell how we can obtain yp from the appearance of f of x. Okay, let's go and understand what we are going to do through an example directly. Okay, so let's assume that we want to find the general solution for this non-homogeneous equation, y double prime minus 4y equals to 8x squared minus 2x. It is routine to find the general solution of the associated homogeneous equation, right? It's very routinely that if you are going to say u double prime minus 4y equal to 0, this is the associated homogeneous equation, you're going to find that we have two distinct roots, for example, which is 2 and minus 2 for the characteristic equation, lambda 1 and lambda 2, and then our solution is going to be, the general solution for the associated homogeneous equation is going to be c1e to 2x plus c2e to minus 2x. This is considered to be the solution. This is like as if y1 and y2 here. Well, this is part now, we have obtained some part of the solution for our non-homogeneous differential equation, but we need the second part, which is the particular solution. We want to add yp, or we want to find yp of the non-homogeneous equation. So if you look to the right hand side here of the equation, you're going to find that it is polynomial. Okay, it is polynomial. So here it tells us something. Okay, whenever f of x, which is 8x squared minus 2x, is a polynomial, and derivatives of polynomials are polynomials as well, because we know this, that if it's a polynomial, then the derivatives of the polynomial It is going to be polynomial as well. So it is reasonable to think that there might be a polynomial solution. That's it, that we are going to think about it. It's by guessing. It's pure guessing here. So because this is polynomial, maybe that the solution of the y or the solution of the equation is going to be polynomial as well. Okay, so let's go and explore more. This reasoning suggests that we try a particular solution yp with this form, which is polynomial form. A x squared plus bx plus c. So this is the form of the particular solution that we are going to guess. It's only guessing. We do not know whether it is right or wrong, but we just guessing, okay, because of the appearance of f of x. Then we're going to compute. What we're going to do simply is we're going to take the derivative of this yp once and twice. So the first derivative and the second derivative, we're going to obtain it. And then we're going to substitute back in the non-homogeneous equation. So we're going to obtain y prime, as you can see it here, which is going to be 2ax plus b. This is the derivative, the first derivative of this right-hand side. And y double prime, which is going to be 2a here. And then we're going to substitute these two into the differential equation. So we have here, this is 2a, which is y double prime. This is y double prime. And this minus 4 times ax squared plus bx plus c. This is 4y, which is from the original differential equation, equal to the right-hand side of the original differential equation, right? Then we can see that it is only, we want to rearrange it, to put it in a good form. So we arrange it in this form, that after rearranging, we can find that here it's a coefficient here, or a term that is multiplied by x squared, another term multiplied by x, and the free term which is without x here. And this equals to the 0, right-hand side. Just we rearranged this into the left-hand side, and we found that this is the end. Now look to this equation. Look to this equation clearly. This seems to be polynomial, right? And it is second-degree polynomial because we have the largest or the highest power here of x is 2. So this means, this suggests that we have two roots only for x. We have two roots only for x in order to equate it with 0. But actually we want a solution for all values of x. All values, not only two values, not only two roots. We want all values of x. Whenever that we put it here, whenever that we substitute with x with any value in this equation, we want the right-hand side to be 0. We want the calculation of this left-hand side equal to 0. This means that these terms or these coefficients must be 0. Okay, because 0 in any value of x plus 0 in any value of x plus 0 would equal to 0, right? So this is what we said here. But a second-degree polynomial has only two roots unless all of its coefficients are 0. These are the coefficients here, which is minus 4a minus 8, minus 4b plus 2, 2a minus 4ac. So each one of them should equal 0 independently. That's what we are putting here. This is the first coefficient equal to 0. This is the second one equal to 0. And this is the third coefficient equal to 0. Now, how many unknowns that we have in this equations, or how many constants that we want to obtain? We have a, we have b, and we have c. But we have three different equations. Then we can solve and get the values of a and b and c. This is what we're going to do here. So a equal to minus 2, b equal to half, and c equal to minus 1. This gives us the particular solution. As you can see, this is the particular solution because we have assumed it before, a times x squared. So a here is minus 2 plus half x, which is b, and then minus 1, which is c. This would give us the general solution of the undetermined coefficient. It is going to be c1, which is e to x, and the second y2, which is of the associated homogeneous equation, and then we are going to write yp, which is the particular solution, Okay, so these are the three ones that we are dealing with. Okay, so I hope that I'm going to recap what I said here. From this f of x, we suggested yp, which is polynomial. Okay, so let's go and see if f of x is not polynomial. Let's see that if f of x is something else. And this is what we're going to have in our next example. Let's find the general solution of this y double prime plus 2y prime minus 3y equals to, yes, we are talking about exponential function here. Exponential function. So this is a second pattern of f of x. It is not polynomial, but it is an exponential function. Well, we are going to go with the same strategy, which is finding the independent linear solutions of the associated homogeneous equation first. You can check this y double prime plus 2y prime minus 3y. The general solution of this homogeneous equation, it is going to be, if you, this is the characteristic equation. It is going to be lambda squared plus 2 lambda minus 3 equal to 0. This means that we have two roots for lambda, lambda 1 and lambda 2. It is going to be minus 3 and 1. Then our solution for the associated homogeneous equation is going to be c1e to minus 3x plus c2e to x. Okay, so this is what we have here for the solution of it. Look to this very carefully, that we have one solution contains e to minus 3x and another solution equals to e to x. Okay, now look for the particular solution. Because the derivatives of e to x, which is here, are constant multiples of e to 2x, we suspect that a constant multiple of e to 2x might serve. Again, might serve. We are guessing, we're guessing. Okay? Then let's try yp, the particular solution, to be a constant a times e to 2x, which is the same function of the f of x. And then let's substitute this into the differential equation. Then we know that yp prime, because it is a, so it is going to be 2 times e to 2x, and y double prime, it is going to be 4a e to 2x. So this is what we are having here. So here, this is y double prime. Here, it is 2y prime, which is this one. Take care, this is 2 times 2, okay? 2 times 2a to ax. And then minus 3y, minus 3, and this is y, which is already, we said it is y particular, okay? Just we substituted y particular into the main non-homogeneous equation after getting the derivative and the second derivative. So we put it like this. Rearrange them. We found that the left-hand side equals to, this is, all of them, they are e to 2x. And there are some coefficients here. So algebraic calculation of this gives us 5a e to 2x. And this would equal to 4 equals to 4 e to 2x, which is the right-hand side. The right-hand side, right? So we are dealing with this now, which is the left-hand side 5a e to 2x equals to the right-hand side 4e to 2x. This means that exactly 5a equals to 4, so a equals to 4 over 5. And the particular solution, which is we already assumed here by guessing, just free guessing, we found that it works here. It is going to be 4e to 2x over 5. Then the general solution is going to be y1 here, already we have obtained it before, y2 here, and yp is going to be here, and this is yp. Okay, this is yp. Okay, now we have these kind of different things. which is, or now the strategy, as I said, that the right hand side was an exponential function. So we suggested that this y particular is going to be an exponential. So you can take it as like this. Whenever the right hand side of the non-homogeneous equation f of x is exponential, then assume y particular equals to a constant times the exponential function. This is the key. Okay, now let's go and jump into another type of the f of x. Okay, let's go to another type. Find the general solution of y double prime minus 5y prime plus 6y equals to, okay, this is f of x here. It is not polynomial, it is not exponential, but it is sinusoidal. It is sine or cosine, for example, okay, sinusoidal. Minus 3 sine 2x. So this is the third type of f of x that we are going to deal with, okay, a sinusoidal equation. Now, routinely, we are going to get the solution of this associated homogeneous equation, constant coefficient case. Very easy for you to get it. So we equate it to 0, and then you can find that we have the roots here is going to be c e c1e to 3x plus c2e to 2x. Okay, so this is the the solution of the associated homogeneous equation. Okay, there are two distinct roots, 3 and 2 for lambda 1 and lambda 2. Now we need a particular solution. Now we are talking about the particular solution. We want yp now of the non-homogeneous equation. So look again to this f of x. What do you think about the sinusoidal? One of the things that is very nice regarding sinusoidal, that the derivative of the sine is cosine and the derivative of the cosine is minus sine. Then they are interchangeable. So here he says derivatives of sine 2x are constant multiples of sine 2x or cosine 2x, right? That's right. So this is the key here, that we have the derivative of the f of x here, or the sine 2x, is multiple or constant multiples of sine 2x or cosine 2x, right? Derivatives of cosine 2x are also constant multiples of sine 2x or cosine 2x. This suggests that we try particular solution as, yes, we are take care of this. Whenever that you have a function which is sinusoidal in the non-homogeneous equation, okay, then the particular solution is going to be two terms. Take care of this. It's not one term only, it is two terms. The first one is going to be a constant times cosine 2x, and the second is going to be pb, another constant, times sine 2x, the function itself that we have. Okay, so this is the form that we are going to deal with. Notice that we include both sine 2x and cosine 2x in this first attempt. Okay, take care of this. Even though f of x just has a sine 2x term, we only have here sine 2x term, but the y particular is going to be assumed in this way, and you are going to know why at the end, because we are going to have the derivatives now, and they are going to cancel one another, as we can see. Okay, so now what is the second step? That we need to obtain y prime and y double prime, and then back substituting in the main non-homogeneous equation. Y prime of a cosine 2x plus b sine 2x is going to be minus 2a sine 2x, this is the first term, which is for this term, plus 2b cosine 2x, which is the derivative of this term. And y double prime p is going to be of x equals to, here we have minus 2a sine 2x, it is going to be minus 4a cosine 2x, and here 2b cosine 2x, it is going to be minus 4b sine 2x. Nice, great. Substitute these, which is y prime and y double prime and y only, into this equation, which is the non-homogeneous equation, and rearrange it. So we have here, this is y double prime, all of these two terms that already we have obtained here, and then minus 5, take care that we have minus here, as you can see. So minus 5 times y prime, which is already we have sorry, this is here, this one, the first term here, it is y double prime, okay? But the second term, which is y prime, it is this term, which is minus 2a sine 2x plus 2b cosine 2x, as you can see. And plus 6y, 6 times y prime, which is, this is y prime, a cosine plus b sine, as you can see, equals to the right-hand side of the non-homogeneous equation, which is minus 3 sine 2x, minus 3 sine 2x. Rearrange all of them, and you're going to find the following. So we are going to rearrange them. So we found that after rearranging, we are going to end up with one term multiplied by sine 2x equals to another term that is multiplied by cosine 2x. Think about this equation. Think about this equation. Is it possible for sine 2x and cosine 2x to be constant multiples of one another? Is it possible? Can we say that, for example, can we say that 3 sine 2x equal to 5 sine or 6 cosine 2x? Okay, no, this would not happen. So the left-hand side will not equal to the right-hand side unless that, what? This term and this term equal to 0. Okay, that's the key. So what is the key? Sine 2x and cosine 2x are not constant multiples of each other unless these constants are 0. That's the key. So here we cannot say that the two sides are equal unless that we are having the coefficients here, or these constants are 0. So based on this, we're going to equate 2b plus 10a plus 3. We're going to equate it to 0. And we are going to equate this, which is minus 2a plus 10b. We're going to equate it to 0 also. Here, we equate it to 0, as you can see. Then we have two equations, and we have two unknowns. We have two equations. The first equation, this one, and this is the second equation. And we have two unknowns, which is a and b. We are going to solve these to get a equal to minus 15 over 52 and b equal to minus 3 over 52. And the particular solution is going to be exactly, this is yp. It is a here times cosine 2x, and this is b here times sine 2x. This is our particular solution. And the general solution is going to be, this is the general solution, is going to be the y1, which is the first linear independent solution of the associated homogeneous equation, and y2, the second linear independent solution of the associated homogeneous equation. And then the last one is going to be yp, which is obtained through the undetermined coefficient through our method for today. Okay, so remember that we are guessing, just we are guessing. We didn't do anything, just we said that yes, yp here is going to be something like this. Who gave us this clue? I'm going to tell you how to obtain this, how to guess, right guessing for yp in general. I'm going to tell you about this, okay, in the steps of the solution. But anyway, now we have an idea of how we can deal with the second, we can deal with the nonlinear homogeneous equation, whether we have polynomial as in the first equation, or exponential function in the second example, or sinusoidal function as in the third example. So we have three different examples with three different patterns of the f of x. Now let's go to understand more about our method and what are the traps that is built in this method. There is something that we want to warn you regarding it. The method of undetermined coefficients has a trap built into it. Okay? We're going to find together now what is the trap built into it. Consider the following. It is general to say that find a particular solution for this non-homogeneous equation. Very easy here. The right-hand side is exponential function, right? And this seems to be constant coefficient homogeneous equation. Very easy to get their associated their solution, right? But as usual, we said reasoning as before, we are going to try y particular to be constant times e to x. Here, we said that it's going to be a to ex. Then substitute this into the differential equation after taking y prime and y double prime from a to e to x and substitute back. It is going to be a e to x, which is y double prime, okay, and this is plus 2y prime minus 3y, as you can see here. Look to this left hand side. It is 0, right? It is 0, and it should equal to 8 e to x, which is the right hand side, which is never 0. So left hand side is 0, but right hand side is never 0. So there's something wrong in this equation. Actually, the wrong thing that our assumption from the beginning, which is y particular equal to a e to x. What is the wrong with this? We already have solved an example before, right? Yes. So the point is, the problem here is e to x that is already contained in our y particular assumption is also a solution of the associated homogeneous equation. Look here, I said to you that this is very easy for you to get the solution for it, right? It's no problem. But actually, if you look deeper into this, you're going to find that e to x is considered to be one solution of the associated homogeneous equation. This says, what is the meaning that this e to x is going to be a solution? This means that the left-hand side is going to be 0 if we use one solution that is containing e to x. And this is what we have done here. We assume that y particular equal to a times e to x. So this is definitely would give us 0. Okay? So the left side will vanish when a e to x is substituted into this equation. That's right. This left-hand side is going to vanish. It's going to be 0 because it's a solution for it from the associated homogeneous equation, right? Whenever a term of a proposed yp is a solution of the associated homogeneous equation, multiply this proposed solution by x. This is the key here. So this is the key. The key that you look to the homogeneous, associated homogeneous equation. If the solution is e to x, then take care. Do not take your yp equal to a to ex. Multiply it by another x here. Okay, so instead of having a times e to x, then take the solution to be a x e to x. This is the right thing. This is the right yp that you should use. Well, if this results in another solution of the associated homogeneous equation multiplied by another x, because sometimes you can find that a x e to x, it also can be a solution for the associated homogeneous equation. In this case, we need to multiply by another x. Okay, let's have an example and see and explore how we can use it. So we're going to revisit problem 2.14. Let's go and see it here. So this is this is 2.14 here, which is this equation, okay? Y double prime plus 2y prime minus 3y equal to 8 e to x. So here, f of x is 8 to x. Our first impulse was to try y p x equal to a x, and we said this would not work for us, right? But this is a solution of the associated homogeneous equation. So multiply by x, that's the key, and try yp equal to ax e to x. This is our new assumption. Now y prime is going to be a e to x plus ax e to x. This is the derivative, right? By the chain rule we can obtain this. This is a first function is x, second function is e to x, then by the chain rules we can obtain this a e to x plus ax e to x. And y double prime, it is going to be the derivative of this. It is going to be 2a e to x plus ax e to x. Substitute these into the differential equation to get then our main differential equation. Already we know it. It's here. This is our main differential equation. Y double prime plus 2y prime minus 3y equal to 8 to x. So here this is y double prime. Here this is y double prime plus 2y prime. Okay. And this is the free term, which is y equal to the right hand side, 8 to x. Now, rearrange the left hand side. You're going to find that left hand side reduces to 4a e to x, and the right hand side as it is, which is 8 e to x. This means that our a is 2. Yielding the particular solution is going to be 2x e to x. Okay, so now this is our solution. This is y particular here. This is y particular that we want to put with other y1 and y2 of the associated homogeneous equation to get the general solution. This is the general solution for us. Okay. Okay, I hope that you understood this, this kind of small trick for the trap built in the undeterminate coefficient, and I hope that you can overcome it. Okay, let's have another example, which is dealing with the same problem, but we are going to go further with it. We want to solve this equation, y double prime minus 6y prime plus 9y equal to 5e to 3x. Okay? The associated homogeneous equation has the characteristic equation y minus 3 to the power 2 equal to 0, with repeated roots, lambda equal to 3. Then we have repeated roots. So the general solution of this associated homogeneous equation is C1, if you remember, we have y1 here, C1e to 3x, and the other solution here is what? Exactly, C2x e to 3x. So our y1 and y2, they are having, one having e to 3x, the other one is having x e to 3x. So this is the solution of the associated homogeneous equation. This means that for our particular solution, let's go and try to guess. First try is going to be y particular equal to a times e to 3x, right? But this is solution of the homogeneous equation, right? Here, this is a solution. So we cannot use the first assumption. Then the strategy says to us, multiply by x and try y particular ax e to 3x. This is also a solution of the homogeneous equation. Here we have this one, c2x e to 3x, so we cannot use it. So multiply by x again, we are going to multiply again and try y particular equal to ax squared e to 3x. If this is substituted into the differential equation, which is the original one here, okay, we obtain, if we are going to, after taking the first derivative and the second derivative of this one, you can do it by yourself, we're going to find that a equal to 5 over 2. So a particular solution is yp equal to 5x squared e to 3x over 2. This is our particular solution, and the general solution is y1 plus y2 plus yp. That's it. This is the general solution for us. Okay, I hope that you can understand now the meaning of how we can go through the different traps of the undeterminate coefficient and when to guess a right guess for the particular solution. A right guess for the particular solution. Okay, now let's go and wrap up this by ending with the main drawbacks of the undeterminate coefficient method. we have two drawbacks actually. The first one is the method of the undetermined coefficient is limited by our ability to guess. This is one of the drawbacks actually. We need to guess every time. We need to guess a particular solution from the form of f of x, which is sometimes it is going to be a little bit difficult, not easy, not straightforward. Okay. Unlike variation of parameters, it requires that the coefficients y prime and y be constant. So we need, it's not suitable for the variation of parameters. It is suitable for the constant coefficient case. Okay. So these are considered to be the two main drawbacks of our method. Let's have the summary of what we have said today and put it as a strategy for the solution. Suppose we want to find the general solution of this equation. This is a very general non-homogeneous equation. First step, write the general solution of which is for the homogeneous equation. Y homogeneous of x equal to c1 y1 plus c2 y2. Okay, this is the solution of the associated homogeneous equation. Then we're going to say that we're going to equate the characteristic equation with 0, and then we can find y1 and y2 linearly independent solutions. We can always do this in constant coefficient. So as I said, this is only suitable for the constant coefficient case, but for the case of variation of parameters, it's not going to work for us. Okay, so take care of this. This is step one. Step two, we need a particular solution yp of the non-homogeneous equation. This may require several steps. You need to make several attempts. Make an initial attempt of general form of a particular solution using f of x. F of x. As I said, whenever that it is polynomial, then you can use a polynomial for particular. If it's exponential, use a constant times exponential. If it's sinusoidal, use a cosine something plus b cosine something, right? And we need to put something which is a table that is considered to be a guide for you. So in this table, this is the form of f of x, and this is the form of yp that might help you for guessing. So if it's polynomial for f of x, then guess or choose yp to be another polynomial. If it is exponential function, then use the exponential function as a guess for yp. If it's sinusoidal, which is starting with cosine, then your suggestion is going for cosine or sine, then your suggestion for y particular, it is c cosine beta x plus d sine beta x. Similar for cosine and sine, they are similar. And if you have something like p of x times e to cx, this is function of x, then assume q of x times e to cx, which is the same exponential function here. Then this is only a table for you to go through. It's a guide for you. It would help you only, okay? If this is not possible, this method cannot be used. So do not make several attempts. As if you cannot find y particular, okay, if the table, you can't find something in the table, for example here, suitable for your case, then do not use this method, which is undetermined coefficient. If we can solve for the constants, so that this first guess works, then we have yp with us. And the next, that step 3, if any term of the first attempt is a solution of the associated homogeneous equation, then you need to multiply it by x first. If any term of this revised attempt is a solution of the homogeneous equation, multiply it by x again, okay? And then substitute this final general form of a particular solution into the differential equation and solve for the constants to get yp. And the general solution is going to be, as you can see it here, which is y1 plus y2 plus yp. Okay, so this is the general steps for the undeterminate coefficient. Okay, now let's go to the in-class assignment. So now we are going to talk about the in-class assignment. So as I said, usually our strategy is something like this, that you are going to look to the problem and stop the video and afterward you are going to solve it, and afterward come back again to the video and see the solution. Okay, so now look only to this part, okay, which is the problem, which is y double prime minus y prime minus 2y equal to 2x squared plus 5. This is a polynomial equation. Then you can start your solution based on this polynomial function. Okay, stop the video and solve this equation and then come back again to the video. Okay, I hope that you do this. Okay, now the solution for this, it is a polynomial. Two independent solutions. First of all, this is the homogeneous equation. It seems that constant coefficients here. So two independent solutions of the associated homogeneous equations are y1 and y2. This is actually solved here. So we have, this is the characteristic equation. Then we have the lambdas that we have. Okay, we have lambda 1, which is equal to 2. Lambda 2 equals to minus 1. Okay, and based on this, we can get or guess here the yp, which is going to be ax squared plus px plus c, because it is polynomial as we said. And then the first derivative is y prime p, and the second derivative y double prime. And then we are going to substitute back in our main equation. Okay, then after substitution you can go through this. This is the substitution in detail, and then you're going to find that a, b, c can be obtained easily, right? So these are the values. I hope that you obtain the same values when you solve it by yourself. This is y of x in this case is going to be the first independent linear solution of the homogeneous differential equation, and y2, and then y particular that is already we have obtained. So based on this, our y particular is minus x squared plus x minus 4, and the general solution is going to be like this, which is this one. Okay, I hope that you have done this, and I hope that you have solved this in the right way. Let's have another example in class assignment. Okay, now let's go to this. Look only to this part. Okay, y double prime minus y prime minus 6y equal to 8 e to x, e to 2x. Now it is exponential function. Then you need to be careful. Look to the associated homogeneous equation and check that y particular that you are going to guess is okay. It is not a solution for this. Okay, so we're going to find the y1 and y2 first of the associated homogeneous equation. So y1 equals to e to 3x, y2 equal to e to minus 2x. Our characteristic equation here is going to be, as you can see here, we have like different distinct roots, 3 and minus 2. Based on this, we can make our assumption for yp a e to 2x, and then we can get y particular prime and y particular double prime, and we can say that they are, none of them is equal to our assumption. So we can go through with this assumption, substitute back in our main equation. This is the substitution and rearrangement. You are going to find that only one unknown, which is a equal to minus 2. Then our y particular is going to be exactly minus 2 times e to 2x. This is y particular. Here we have y1 and y2 as we said before for the general solution. Okay, these are the two in-class assignments. You need to do the home assignment after that. Two problems, you need to go through them. This is the first one. Y double prime minus 4y prime equals to something like this. Okay, 8x squared plus 2e to 3x. Okay, maybe you need to use the table here. And the second is, this is the second, y double prime minus 4y prime plus 13y equals to 3e to x minus 5 to 3x. Okay, you need also maybe to use the table. Okay, these are the two examples or two homeworks that you need to submit. Okay, now let's go This is for today's lecture. I hope that you understood clearly the undeterminate coefficient, and I hope that you can work by yourself for the home problems and also the in-class assignments. Thank you and see you next time.